Hi, this is Darsh and Louise. We're students of MIT's Computational Material Design class taught by Professor Olson. And today we're presenting our project on the multi-objective design of an ultra-high-strength aluminum plate alloy, which is a collaboration between MIT and the DSO labs in Singapore. So we want to develop a high-strength aluminum plate with 10 centimeter thickness that's fabricated by the conventional casting and wrought processing and has applications in aerospace and automotive industry. So here in the Ashby plot, we can see for the 7000 series aluminum alloys, we have the target in the pink circle. We want to have a yield strength of 750 megapascals and an elongation between 12 and 15%. Additionally, we'd like to improve the stress corrosion cracking resistance, the quench sensitivity resistance, as well as the fracture toughness.
In order to reach these objectives, we first create our system chart, which shows the relationship between processing structure, properties, and performance. So in order to achieve high strength and good quench sensitivity resistance, we use a co-precipitation strategy focusing on co-precipitation of our metastable phases at our peak aging conditions. And to improve ductility and toughness and stress corrosion cracking resistance, we want to inhibit recrystallization and enhance grain boundary cohesion.
So that being said, here's our design approach. First, we want to maximize strength. So we develop an order one strengthening model to predict the yield strength at the peak hardness. And at the same time, we apply constraints to improve the quench sensitivity resistance. Then to inhibit the recrystallization, we want to maximize the Zinner pinning force exerted by the coherent L12 phases. So we introduce scandium and zirconium into our system for that. For the calculations, we employ thermocalc software and the databases. Lastly, to enhance the grain boundary cohesion, we try to maximize the interfacial work of separation between the grain boundaries, and we perform thermodynamic calculations combined with high throughput DFT data that's collected from literature for our calculations.
So for our design, we focus on this blue region over here in the phase diagram. And this is going to be where eta prime, S prime, and T prime all will co-precipitate. And the advantage of designing within this blue region is that our solid solution strengthening portion is going to be fixed. And so it'll only matter to optimize our precipitation strengthening component. And so then next, we calibrated our OR1 strengthening model with data from literature against thermocalc data. And then we selected a 7A93 alloy in order to experimentally validate our results. Examining the metallography revealed that the intermetallic particles rich in the iron and copper lie segregate to the grain boundaries and remain undissolved after homogenization steps, while in the tensile tests, they showed premature fracture. So for our design, we wanted to have a wider solution temperature window in order for these phases to dissolve fully. So next in the selected design space, we calculated the precipitation strengthening contribution of each of these three strengthening phases and the total precipitation strengthening as shown in these four plots over here. And we observed that the most effective phase for strengthening is going to be the eta prime phase, which is rich in zinc. To improve quench sensitivity resistance, we performed some Prisma calculations with our thermocalc databases, and specifically, we set the 785 alloy with eta phase and the 775 alloy with our T phase as the best and worst case scenarios for our parametric design approach, where the worst case is this orange and the best case is this green.
And lastly, for our objective to improve the stress corrosion cracking resistance, we employed the thermodynamic Rice-Wang model, for which we collected DFT data to investigate the contribution of elements to the grain boundary cohesion. So our analysis revealed that the main contribution to grain boundary cohesion derives from the zinc, which has a negative effect, and from the magnesium and copper, which have a positive effect.
Finally, for integrating all of these design components, we had two steps. In our first step, we used a multi-objective genetic algorithm in the aluminum, magnesium, zinc, copper system in order to maximize our total precipitation strengthening and our grain boundary cohesion. And then we determined a list of optimal solutions for these two parameters. In order to have a solution temperature window greater than 30 degrees, we selected this composition right here as denoted by the red circle.
And in the second step, for a fixed magnesium, zinc, and copper composition, we determined the optimum content of the scandium and zirconium that satisfies our constraints for a minimized normalized coarsening rate of the L12 phases while having the enough fraction to inhibit recrystallization. So those constraints are shown in the shaded areas. And our final solution is given in this table below, where most importantly, our target total yield strength of 750 megapascals is achieved.
That was our project, and thank you all for listening.